We're going to start the next session. It's with German, going to talk about model evaluation and cross-validation.
Yep, I was at the workshop yesterday, I think, and I think Nona asked if you know what is cross-validation, and everyone answered, yes, we know. So maybe I should skip this. Cross-validation, everyone knows what is cross-validation. Like half of my workshop is kind of gone. We can go to have lunch earlier. It will be very basic. It will be a lot of theory here because I think previously this basic theory wasn't really explained, and I think some people here they don't really have the background, so I have to repeat things again. So maybe for the people who are advanced, it won't be so useful. Let me check. So yeah, it's first I will do a short introduction, then I will talk about how to evaluate models and cross-validation, all basic stuff here. There was a bit of, I work for a consortia in my main job, so there was a bit of mix-up there. I asked them if I can use the slides from this consortia for the conference after the school. But they misunderstood it. They thought that today present not only workshop, but also my work at this consortia there. And it was released only yesterday, and in Germany, you know that on Saturday or Sunday no one works, so I couldn't fix it at all. So it's kind of false advertisement, but I can also speak about this consortia, SOVRD, it's called So Rare Disease. It's about the big data in rare disease. Rare disease means like that maybe 100% in the world have this particular disease, or even 10. So when we speak about big data, what do we mean in this sense? It's a huge collaboration all around Europe and America, a bit because these rare cases, they have to be collected by the clinicians and the unfortunately, in Central Europe, it's only Czech Republic is represented here, but it's mostly like France, Spain, Germany, and Britain, as you can see. Yeah, in the types of data there. So for a doctor, when you evaluate the rare disease phenotype there's very specific data here. So it's rarely known which disease this person, which disease this person have in this SOVRD. So like we're trying to solve unsolved cases here. So you have to describe phenotype there, and you have to find the matching between phenotypes. So there's a lot of space for machine learning. So if people vote for me to present this like big data in rare disease medical genetics, I can prepare the presentation because otherwise it will be false advertisement here on Twitter, and yeah, it won't be so good. So again, machine learning is big, and we'll be talking about only two things. It's classification and regression here. We don't talk about clustering evaluation and anything else. Yeah, so this it's basic notation. Data sets will have vectors of data here, so I will be using this notation further. What is evaluation metric is, it's a way to quantify the performance of your model. We need to compare our model with other models, and also we need this evaluation metrics for tuning our models, for choosing hyperparameters. Yeah, disclaimer, everything I took from somewhere, so there is almost nothing created by me personally. Yeah, this you've seen yesterday, it's the regression model that's called written. It's the, I will call the y variable as response, and I will create x, call x matrix as the predictor here. And there's error term. This is very important because there is a, you discussed already yesterday that there's an irreducible error here. So the types of the problems we'll be talking about is the continuous outcome regression. Ordinal outcome regression we will not be talking about, but in the beginning, when you work with ordinal data, I always use the standard MRC first. If it works fine, then it's okay. There are specific metrics for them, but we won't touch it today. And first of classification, we'll discuss the pro and contra of all these other metrics listed here. I come more from statistical background, so we had a kind of argument about this during the first panel discussion about inference and prediction. I still stand on my ground, so I think that I belong to this camp, and but today we will be talking about the another one. So we'll be talking about the evaluation of the in the context of prediction in terms of the performance of the model on unseen data. Just example from modern biomedicine. GWAS, when we do GWAS, I consider this as the statistical, like people use statistical approaches to GWAS. here, and they don't really aim at prediction. They, of course, aim at the reproducibility of the results, but they don't predict kind of anything with GWAS. But from GWAS, we can switch to polygenic risk scores, and then it turns into the prediction problem. So we can evaluate the risks of the, for example, for cardiovascular disease from these small risk markers here. So it's kind of same data, but a very different approach. One is statistics, understanding which gene is actually connected with this significant SNP in GWAS results. And another one is the just prediction. So, as I said, for example, confounding. When we do prediction, we don't really care about confounding. And when we do inference, it's very critically important to discover what affects what here. Otherwise, it's not a qualitative inference. All the plots I will be showing today will look like this. So there will be one plot which is making U-shape and another plot which goes down. What does it mean? We have two types of error. One error that we obtain on the train set, and another type of error that we obtain on test set. Training error when we increase the model complexity here. So we add more predictors like square terms, interactions, and the additional parameters in the model. We increase the complexity. And if we try to evaluate our model on the data we use for training, it will be always better and better. But the tester, at some point, the tester will stop decreasing, and at some point we'll have to stop. So this evaluation model is really required to find this sweet spot, to this best fit, so to minimize the test error here. Let's talk about regression first. We have continuous outcome, and we'll be talking about three particular metrics. Mainly, it's the R-squared. Coefficient of determination, root mean squared error. You already kind of discussed this. We discussed a bit more details, and the mean absolute error. These are just popular metrics to evaluate models in the biomedical papers, I would say. For example, in GWAS, it's typical to describe each SNP with the R-squared associated with the SNP here. Again, residuals is the distances from the data points to the regression line. Why the residuals are not perpendicular in this case? So it seems natural to make them perpendicular because it's a short distance to the fit to the model. Because we assume that the errors occurs only in the response. We think that here in the predictors there are no errors. If we assume that there are errors here, it's another class of models. It's like totally squares. And it's a kind of different theory, but in this formulation, the error is only in the response here. So we have these residuals, which are distances, vertical distances from the data point to the fitted line here. Scary formulas. I think they're actually really easy here. So on top, it's written the mean of the outcome. Then it's there are two components, which is sum of residuals. There's total sum. And this sum of residuals, you calculate them, and formula to find the coefficient of determination is 1 minus the ratio between them two. There's a really simple geometrical explanation for this. The model on the left is the neutral model. So imagine you have no predictors here. So for example, you ask me like, there's a person staying in the next room, what's the height of this person? I have no predictors, I know it's only humans, so I choose the average of the height of the general population. I say like 170 centimeters. It's just like, I don't know, but then you, for example, you give me predictors, like the person is from like Netherlands, and I mean like maybe 175, maybe they're a bit taller in general. And then you add me additional predictors, and I start to adjust my prediction. So this is the neutral model. This is, I know nothing. I don't have any predictors. This is just average of the outcome. Here, this is the best guess I can make in terms of this RMSE metric is the average. And this is when we feed the model with the predictor X. In this case, it's like a linear regression with only one predictor. It's difficult maybe to see, but there are also the super small squares here, here, and this one is possible to see. So you take these squares, you take this area, you sum them up, and it will make this blue term here. So it's basically a ratio between these areas here. distances from the data points to the fit line squared. And if this sum of squares total big and sum of residuals is small, we get big R squared. Our kind of the good model, which explains a lot of variance, is called explained variance. This R squared is closer to 1. Let's call it to 1. It's not always possible. In the psychology research, for example, R squared of like 0.6, 0.4 are already considered good. So it's not, if you see bad R squared, it doesn't mean the research that was done is bad. Sometimes it's just really difficult to predict. Sometimes there is a lot of noise, a lot of things that you cannot include in the model. Like in psychology, indeed, it's a super complex field where we cannot measure things very accurately. So there is no such thing as the bad R squared. It's better it to be closer to 1, but it depends on the area here. Drawbacks. All these three models here, they have the same R squared. So they explain the same percentage of variability. It's famous Anscombe quartet. Yes, so kind of question, which model is the best? We cannot answer this question because they fit to different data. We can evaluate model only on the same data. When you measure R squared, you need to be sure that your assumptions are adequate about the model. Otherwise, you may end up here, you may find that your model has high R squared, but for example, only because of one like outlier, something like this. No, it was actually this case, because of one outlier. Okay, so let's do experiment. I put code. I didn't provide the listings of the code, so you cannot copy and paste them. You have to write it yourself in R. Like if you can do it in Python, do it in Python. I just really scikit-learn. I don't really know how to extract R squared from the linear model there. R squared and Java R squared. What we do here, I need to explain the concept. First line, we set seed. We want to have reproducible results. So we always before we do anything random, we set seed. Then we simulate outcome. Absolutely random normal variable. Our norm is give you 100 numbers from the standard normal distribution, which has mean of 0 and standard deviation of 1. So you generate outcome and totally random predictor, and you feed the linear model to this. So let's do this, and summary of this linear model. You don't need to copy it. If you can write it better than me, it's not a good code. Later you will see why, because there will be 4 cycles. If you can write it differently, this is tilde. This is symbol in LaTeX. In this verbatim mode, it does not do it. So make this summary, and let's see what you will get. This is the quality of the model. I will return back. Why I don't make it copy and paste? Because personally, if I copy and paste something, I don't really learn. It's like my issue. So that's why I want everyone to kind of to do it yourself. You don't. This is like example solution. If you can do it better or differently, just do it differently. Like for example, here you may generate the whole data set, like whole matrix of random normal distribution. And you can iterate with this as a data set, it's just an example. So let me know, it worked for everyone, right? If it didn't work, then you may ask the neighbor, for example, the person who sits next to you for help. So we get something like this. This is the standard output. We can look at the R squared. This multiple R squared, which is really, really low, it's close to 0. If it's close to 0, then it's a hint that maybe the model explains nothing. In this case, p-value, significance of the regression is 0.99. If you have p-value close to 1, normally people look only at p-values which are close to 0. Like 0.01 is significant result. If your p-value is so close to 1, it can give you some other hints. For example, if you use one-sided test and you have p-value close to 1, it may indicate that your side is wrong. So you used the one-sided test wrong. It's not smaller but bigger, for example. And another thing it can indicate is that the data is falsified. The data was simulated. That's what actually happened. So if the data are too good, they fit too good, the p-value is like super close to 1, it may show that everything was faked. What we do here, in the cycle from 1 to 50, we generate new random variables, and we put them in the regression model. In the beginning, we create a vector where we keep our R-squared coefficient, our metric of the explained variability. We put it into vector, there's only one number here, but then in the cycle, we generate a new and new predictors up to 50. We have 100 samples here. So we create 50 new random, absolutely random predictors, like 100 random normal variables here. And we fit linear model here, it's normal linear model, and we put this R-squared there, and plot it in there. If it's too fast, if it's too difficult, I really recommend to cooperate together with someone who sits next to you, who kind of, if someone next to you is kind of, but in theory it should be quite easy. The right way to generate it is of course not to do cycle, it's of course to generate it from the beginning, the whole matrix. We'll do it a bit later. Were you able to generate the plot? Tell me when you generate the plot of this R-squared. Like this will be R-squared from the models with more and more random predictors. Yeah. C bind is the binding of two columns. So we have two vectors, and we just bind them one to another.
What is the difference between C bind and just C these two?
C creates a vector. C combines a vector, and C bind creates mappings. Okay. I think. C is a shortcut from combine. So something like R was written by a non-programmist, and instead of creating something normal like vector, they like combine. Because C, that's why it's like you combine everything in the vector. So it's quite counterintuitive why it's C. Here we basically push in the end of the vector the new R-squared. So in each cycle we push one more, R-squared, one more. This dollar sign is we ask this object summary of new LM for the field R-squared. The value from this field to extract, because we're interested in this. It's nice if you say somewhere this code, because probably we'll have to use it one step further. So if you write it in the command line, better maybe in Vim or something. If anyone made the plot, just raise your hand. Okay, you did. When half of us will make the plot, we'll move further.
Why you don't use apply?
Because I think I came from C into program. I use apply, but in this particular case, I decided to use it in for. When someone finishes, raise your hand. Good. Almost half. Okay. Couple more. What we are doing here, we're predicting random numbers with random numbers. That's a very easy thing. Okay, done. Who else? Who else? One more done. I think we can move. Yes, we can move. Sorry if it's too fast. The slides I will send out later. And anyway, I will show the result now. So you can see the R-squared, when we add some random stuff, R-squared is growing. So we added all 50 features and we already have quite nice model which predicts like 0.5 R squared. It's actually not so bad. Here it's the correlation of 0.7. Which means if you see something, some R squared, some good R squared in your model, it doesn't necessarily mean that your model is meaningful, the predictor is meaningful. So never do this mistake, never report this simple R squared. Even on random data, it grows really fast. Like I was personally a bit surprised when I saw how fast it grows. We had random variables and we still explain more. What can help us in this situation? We can use this adjusted R squared. It's adjusts for it's a statistical method. It's a bit more complicated than this formula here. It's just in the simplistic form. There are different methods to calculate this adjusted R squared. You punish for the number of predictors, more or less. So if you can change in this particular script, if you can change this R squared, this one, if you can change this to adj R squared, which is adjusted R squared, make the same plot, but with adjusted R squared. Like that. Will it solve the problem? That's the question. So you can see it's all whichever garbage you add, it doesn't increase the R squared, it remains around 0 here. And sometimes it goes even a bit negative in this case. It's fine, negative R squared, it sounds R squared, like something is squared, that like it cannot be negative if it's squared. But it actually can be in many cases. For example, if you calculate this R squared on the unseen data, which we'll do a bit later, it can be negative. So yeah, you see, never evaluate model, if it's multiple regression, never evaluate it with the R squared. Always use either adjusted R squared or more sophisticated method, like cross-validation or like test train approach. I had to say a bit about the Bayesian information criteria, archaic information criteria. These are different ways to penalize for the number of predictors. Like to choose the best model, taking into account the number of predictors, like complexity of your model that you hear. These are not for model evaluation, these are for model selection. If you fit some model and you report like my bit was minus 1,700, it means absolutely nothing in this case. It's meaningful only within one model, only within one data set. Like if you use the same data, then you can operate with likelihood as a value. So this one, like for religious reasons, I use Bayesian information criteria, not archaic, but I really don't know which one is better. You can use whatever. So this is another way to select the best model among the model with a lot of predictors. Not with R squared, but this information criteria here. Not for evaluation. Then let's try to predict some data set, some kind of real data set. This is data set from NGSchool diamonds. In the package random forest, we will use random forest. You will learn exactly what random forest is a bit later. Most probably you know. Yeah, but in details it will be tomorrow, I think, the workshop. The day after tomorrow. I'm not going into details. Now we operate with random forest, like with the black box. Here, so you simply fit random forest on the data, and you look at the this R squared is also percentage of variant explained here. So we need to get this result. We need to get this percentage. I think it's also good to set seed. I didn't put set seed in the beginning, but if you do it really kind of in a nice way, you always have to set seed before randomization. And random forest, it contains randomization, because if you run it, you'll get different result. It's a small data set, it should work fairly fine. So percentage of variant explained should be around 95%, which is incredibly a lot. It's really good. Yeah, it's just like three lines. This is common because it didn't fit into the one script. This 4 lines, sorry. I think everyone typed this. So this is the way to calculate random forest. Random forest. Yeah, let's see. Calculate random forest manually. No, this is the way to calculate R-squared manually. You need to have actual data, your actual response, and predicted values from your model. You use method predict to run your RF model, random forest model, on that data set. So you calculate. You just call, you take actual values of the response, you take predicted value of the response, and this formula will give you correlation between these two values. I think it gives you R-squared correlation. The question is, did you get the same number with the manual calculation and the calculation in the random forest? This is mathematical formula which was shown before, just written in the R language. So this thing is the to the degree of 2, power of 2 here. So is the value that we got bigger or smaller than the one reported by random forest? Bigger. It is. So it's kind of. It's bigger, right?
Yeah, it's all the way around. So
yeah.
It's different.
Yeah, it's different. Why? Despite the fact that R-squared is called percentage of variable explained and the method returned you percentage of variable explained, these are a bit different things. This, in this case, is pseudo R-squared, which is a complex thing. Here in random forest, you have trees, you have features, you have out of back, you select each time a random number of variables. And it has to be corrected. All this added complexity has to be corrected in this case. So this percentage variant explains sounds the same as R-squared, but it's a very different thing. It's pseudo R-squared. So always try to evaluate your model, like if it's complex model, something more complex than linear regression with one predictor. Always use these specialized methods because they have some mathematics underlying, and if you try to do something by definition, how it's defined, you may get absolutely wrong numbers. Okay, so in this case, in this particular, this is a bit longer example. What we do here, let me explain what's going on here. We generate a matrix of 200 200 by 100, 200 samples, 100 features. All of them will be correlated. We generated everything with correlation 0.75. So this is how it's specified the mean. This is how the sigma matrix is specified. You can put proper matrix inside, of course. But in this case, we use like everything for these 100 features is 0 mean, 1 is standard deviation, this is correlation. So all our variables will be correlated in this matrix. So now we will try to, like all these predictors will be informative for our prediction. Now we will see how our method will behave. Now what we do, now we calculate R squared on the, using test data. So we don't calculate R squared on the trained data as we did before. Now we use on the test data. The percentage of variance in the random forest, I think it's also out of bag error there. So it's also kind of unseen data there. But anyway, for us it will be, here we divide into test and train, our big matrix in test and train, and run linear model. This dot means that all the predictors which are in this matrix are used for the prediction. So we have 100 meaningful features. Each of them are correlated with our outcome. You can check it, better check it. Like take like predictor number 5 and check the correlation with the response to the predictor number 1. You run the command core, open the brackets, like predictor 1, predictor 2. And you will see that they actually correlate. You can plot them also, to be sure. This is another way to calculate R squared. You calculate correlation between the predicted values and the actual values on the test set, and you square them, and you will get R squared. This one also you may check. So in this particular case, what intuition tells us, with each new predictor which is correlated with our variable of interest, our accuracy should be increasing. Like my intuition, for example, says this. We don't add the random numbers anymore. Let me know if someone was able to make this. But you may change the correlation number, for example, to 0.8, 0.5. And test this, how it looks like on different correlations. How the strength of a relationship between the response and the predictor define the quality of the model, final model. Raise your hand if you were able to plot it. If you want, one, okay. So far 4. Let's read a bit more. Done. Whenever someone finishes, just raise the hand, and I will say, okay, done, good.
What function are norm multi-done? What is the function are norm multi?
This one is R norm as generate of a sample from normal variable. Multi is like multi-collinear, something like this. So you can generate multi-dimensional normal variables with the predefined correlations. You can choose correlation for each predictor separately. Just for simplicity, I chose everything correlated between each other, like with the 0.75. Put 0.8, put 0.9. Who else finished? Plotted? Good. Good. I think, should I switch to the next slide?
No.
No? Okay. Too fast, too fast. And for others who already finished, think why it is like this. Like you see what's happening with the performance of the model on the test set, on the unseen data. Why? Don't answer yet because some people didn't finish. If something is unclear in syntax, I can explain. Just ask. Did it work? Did it work? It worked, right? Good. This is how the performance evaluated. First, we add one predictor, R squared goes upper. Another predictor, it goes higher, higher, higher. So it's like up to like 20 predictors. All of them are correlated. Everything goes fine. But what happens next? The performance starts to drop, 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 and then it goes to 0. Like it loses the predictive ability. What happened here? You had regression already yesterday. What was the problem?
Multicollinearity.
Yes, it's multicollinearity, so coefficients become really unstable. If you run your linear model with a lot of correlated predictors, you may expect something like this. Performance will degrade. Really, in this case it was 20, and you can modify correlation here to see how it will affect your particular model. For example, if you work in psychology research, you can put 0.5 here. If you work in like more well-defined research, you put higher correlation, and you will see when the model actually breaks due to this multicollinearity. Can we fix it? The answer for everything is random forest. So change linear model to random forest here and see how it works. Random forest is kind of famous that it can deal with multicollinearity. Again, it's R squared calculated on the test set, not on the train set. So it worked? It worked for everyone? Yep. I can show the plot, basically. Yeah, it's one change. One change here, which is like LM, change to random forest. That's it. Everything same as before. Yeah. So that's the performance of the model. So we start fine, then we improve, and then in the end we get what's kind of the lesson from here. Random forest can do with multicollinearity, but it does matter how many predictors containing the same information you put. So they are correlated with your response, but they explain the same variance here. So it doesn't matter how many of these predictors you put in the model. It's not improving. You cannot extract the missing variability from there. So the question is, like, as I was saying in this discussion in the beginning, I took part in the large epidemiological study where, for example, there are 5 different measures of blood pressure. They all are super correlated and they're not adding anything new, but the people who made this, they kind of paid for doctors to take all this analysis. So they were kind of, but we pay, like, let's include everything, maybe it will predict better than, no. If you have the same information, it's not helping. You may kind of reduce the error in this predictor and this blood pressure, even though it's quite accurate, so it's not really necessary. You may average all these values, so it kind of makes you a bit more accurate estimation of blood pressure. But adding all of the predictors just because more predictors, better prediction, it's not the case. So R squared has intuitive scale. So it's from 0 to 1. 1 is amazing. 0 is nothing. It's kind of, it doesn't prove that there is no that your model has 0 where it's explained. It can be due to random reasons, but overall it indicates that there is something wrong here. But R squared doesn't give you any information about prediction error. For example, if you scale y, if you multiply by 100 or you divide by 100 your response. Oh my God, it's my Citrix. Yeah, so to quantify the error in predictions, you use this residual mean square error metric. Some people use this mean absolute error metric, which is instead of summing up squared values divided by the number of these values and taking square root, you just take module. So you just take the distance here. Why it's better, why it's worse? Many people advocate for using mean absolute error for evaluation methods instead of RMSE. It's because it's quite better in terms of outliers. It's much less affected by the outliers than R squared. These are the loss functions for different metrics for evaluation of regression. First is this residual mean squared error. It's a standard ordinary least squared regression. So you can see further from the fitted line, higher the penalty. So it really penalizes a lot for the outliers, for something that is far from your regression line. So it will try to fit your regression line closer to this value. Absolute errors, which was with model, it looks like this. So even if you're far from the regression line, you are not penalized amazingly high. So it's not really increasing like dramatically like squared here. So if you work with the outliers, if you know that you did contain outliers, like NGS data often does, better use this. There is no closed form for absolute error, so you'll have to fit the model with using these optimization techniques there. So some nice things, some bad things. These likelihood approaches, they work quite well, but they take sometimes a lot of time. Winsorized residuals, what it is, you take part from this, you cut parabola from here, and you take ends from this. So it's like it contains the best things from two different metrics. It takes the best from the RMSE in terms of fit to the closest values, and it takes the best from the absolute error, so it kind of tries to ignore the outliers. This one, if you this metric is kind of good if you have extreme outliers. If you think that yeah, maybe something totally wrong, it just gives the equal weight to outliers no matter how far it is. Yeah, so as I said, there are different opinions which metric you should use. I would say MRC in most of the time. If you don't have outliers, most of the time it works quite well. So here it's basically pulled from this famous book, Introduction to Statistical Learning. We have a generative model which is black here. You see, generative model, it's like it's a nature. It's not nature of this data. It's not linear. The data was simulated out of this black model, and then we try to fit other models which show in different colors. If we fit linear regression with like no quadratic terms, nothing, it's just like one predictor, which is orange. Then we fit, I think, with one quadratic term. This is blue one. It can be seen here. The blue goes like this. We're pretty similar to the black line, and the other one you included a lot of predictors, and you see it's like it's jumping really crazy here. So here we have tester and the trainer. For the model which we overfitted, we definitely overfitted, we see that MRC on the trained data is really, really small because we almost went through all these dots here, but the trainer, the tester is really high. And linear model, in this case, we can see that it's inadequate. So here we have to add some quadratic terms and polynomial here. What we have to discuss, like when we evaluate the model, we have to always keep in mind the three things. Bias, variance, and the error that we cannot remove. So variance is the change in the model. So if you train the same model on different data set, and if the model is like close to what you have right now, then it has low variance. If it can fluctuate crazily, that it has higher variance, and the bias is the term which is introduced by imperfection of your model. Like you have to simplify. You cannot be model nature perfectly. So you have always to simplify this due to various reasons. Here again, as I said, there are all the plots look more or less like this. Here you also see the U shape, which is the sum of the bias error introduced by bias and error introduced by variance. And this spot here is basically the balance between the bias and variance here. This is another case, so we can see the black model, which is the generative model. It's not linear. If you look at this, it's banded a bit but it's approximated quite okay with linear regression. So like there are no right models, but there are useful models. And even with simple linear regression, even though the nature is different, we fit quite well here. You can see the rest and trainer is quite fine in this case. We finish with the regression. So this R squared and the residual RMSE, these are metrics that we use. And now you can see when they may lie. Now the classification problem, so you have different classes. For simplicity, we'll be talking about two classes, B-binary classification. We'll talk a bit about multi-class classification in the end, but mostly about, so accuracy is the easiest method. You take all the, let's say we distinguish cats and dogs. We take all the numbers when we correctly guess cat or dog, and divide by the total number of attempts we made, total number of predictions. Is accuracy of 99% good? Not always, yes. The answer is like, for example, we have 1% of people who have the disease. And if we classify all the people as the healthy, we'll have accuracy 99%. So it can be extremely biased, like this method is, never use it. What can I say? Yep. So you don't need to type this. I think it's it's just to show. It's like again we take the data set, we divide it into train and test samples. Here is the credit card default data set. I think it's from this Introduction to Statistical Learning package. Here we divide our sample into train and test, and we fit linear regression, logistic linear regression to this. We predict the outcome. What I want to show you is the confusion matrix. Confusion matrix is the labels that your classifier predicted versus the real labels. Here and then you can guess. You can calculate this matrix, like we will be calculating all these metrics based on the confusion matrices. Why there are two confusion matrices? Your classifier gives you, for example, logistic regression gives you probability of this instance of this sample to belong to particular class, as I remember. And then you may move these thresholds if you want to perfectly predict dogs or perfectly predict cats. You may move the threshold. So you see that I added here the threshold. There is a procedure for choosing optimal thresholds here. This is the comment, optimal cutoff. Here it's from the package information value, or from caret, I think. Yep. So what can you can optimize for accuracy, for example. By default, it's like takes the probability which is given by linear regression. Everything which is higher than 0.5 belongs to class 1, lower belongs to class 0. Or, for example, you can optimize for ones. So you care about one class, about for example, disease classes. Sometimes it's really important. For example, when we work with this mass screening of people, for example, for heart disease, for the future cardiovascular incidents. Let's say we have to examine 1,000 people to find 100. We have to send 1,000 people for additional screening to find 100 people who will actually have this incident in the future. Okay, so sometimes we're really interested in super biased cutoff for these confusion matrices. In this case, we just wanted to detect as many sick people as possible, no matter how many healthy people we additionally screen for this. Usually it's, of course, other considerations other than statistical come into the game. It's like the costs, the psychological cost for the patient. So it's not mathematics anymore in this case. It's like cost-benefit analysis is still mathematics, but other policy effects, like the psychological effects, are not mathematics anymore. There is no function in R which can calculate it for you. So this is scary thing. This is the table from Wikipedia, which I always open when I need to remember what is true positive, what is precision, what is recall. I never remember them. So I always, this matrix is something that I opened maybe several thousand times. Here, I will be talking mainly about the precision, which is here. One means full discovery, and recall, which is here, true positive rate. 1 minus full scientific rate. But there are other matrices here. Accuracy is here, for example. You can see how they are connected in this matrix. I really recommend to spend some time meditating, looking at this matrix. So this is the definition of precision and recall. We'll be working with them. Instead of accuracy, again, what's more important, true positives or false negatives? It's up to you. To help in this decision, there are tools called the receiver operation curve. The name tells absolutely nothing about the method itself. So this is absolutely awful naming. I don't know, like who called it rock? I know. So this is the F1 score. It's also very popular in the machine learning papers. You can see it. It's harmonic mean of the precision and recall. Why is harmonic mean? I have no idea. Just someone came with a deal. Let's make it harmonic mean. Why it can be bad? Why it can be good? This is scary thing. This is absolutely scary thing. This is matrix correlation coefficient. Here, it's widely used by the data analysts. Here, why it's used instead of the F1 score. I will show a couple of examples. So you can see our predictors, our predictor predicted nothing as zeros. We have accuracy 95%, super good accuracy, even though our predictor tells like everything is, everyone has disease. F1 score is super high, 0.1 here. This matrix correlation coefficient is undefined because it's division by 0 here. But let's look at other examples. Again, there are some, the table is not, doesn't contain zeros in some anymore. So we have amazing accuracy, amazing F1 score, and really low this correlation coefficient. What happened next? We switch labels. We switch zeros and ones in the beginning. What we previously considered as a positive class, now we consider as negative class, and vice versa. What happens? It's like our data remain the same. It's absolutely the same. Like, why should anything change? F1 score is very sensitive to this. F1 score is like same matrix, just switch the labels. And you see that the F1 score is changed dramatically. Accuracy remains the same, but accuracy, as we know, we don't use it at all. So this matrix correlation coefficient is summarizing data a bit better than the F1. So many people now prefer to use this one. Receiver operation curve, you've seen it a lot of times, I think. You've seen we plot false positive rate against true positive rate, and we move the threshold of our classifier, and we plot all the precision and recall values for all the threshold values, from minimum, where everything is positive, to maximum, when everything is negative here. So we either get perfect precision or imperfect recall, and then we look something in the middle here. So if our classifier is absolutely random, we have binary class, but if you throw the coin instead of actual prediction, then you will have like the line, this diagonal line, which like area under the curve will be 0.5. It means your classifier is absolutely garbage here, and then it improves more and more. Again, it depends on the field. Like if you see area under the curve is like 0.6, don't say the classifier is bad. Maybe the field is difficult. Here, maybe like psychology, in psychology is okay still. And in NGS, for example, if you do variant calling, SNP calling in the NGS data, now it's closer to the, if you speak about short variants, about SNPs, it's closer to the perfect classifier. Now it's like 0.99 is normal numbers there. So even these examples, they sometimes occur. So now the fight in this NGS field of variant calling is for the last like percentages. So like they apply deep learning, something just to increase this area under the curve by 0.01% or something like this. Yeah, the higher the curve, better the classifier. If your curve goes down, if your curves go here, then you flip the classes. Then at some point you made the coding mistake and you called zeros and ones. It's like just flip the classes. If you predict everything wrong, then it's actually good because you may flip the class. There is a really nice post which explains how to build a ROC curve by hand. Why I recommend this? Because to understand each method, I really like personally, I like to even to write it on the sheet of paper, all these calculations. So it's like blog post. This is the scary code. I just use two libraries. Why I do this? Don't need to reproduce it. It produces really ugly plot. This plot, I wouldn't like anyone to put in the paper, but what it produces, it produces the confidence intervals. You should always remember that this area in the curve, it also depends on the train set, so it's not a stable value. And whenever in the this machine learning conferences, it's quite often, I got several papers for revision there because they belong to like biomedical data. That's why like all my friends who do machine learning, they think that I'm really perfect reviewer for these papers. Even though it's not my field, it's not genetics or something, they still send it to me. And sometimes they say like, in previous paper, the AUC was 0.975, and we achieved 976. They don't put confidence interval, they put nothing. And for me, it's like, how long you will select in the random seed to get this result. You definitely were cheating with the random seed. Yeah, I've seen this in some collaborators. They actually like, I don't really like this random seed. My results are not, I will change it to my year of birth. No, it's also not good. I will change to square root of 2 or something like this. So people actually do this. And when you see the AUC report, it has the like just 1 point estimate. You always have to think that there is also uncertainty in the estimation. Why AUC and ROC can be problematic? These are examples of two classifiers here, which on the left side we have the zero operating curve with true positive and false positive rate on the X and Y, and here you see precision and recall. What happened here? We have imbalanced data, we have severely imbalanced data. AUC, this zero operating curve, it doesn't care about the imbalance in data. It's actually desirable property. It's actually quite good. If you don't care about the minority class more than you care about the majority class, AUC is a perfect tool to, like in many blog posts, they write something like, don't use receiver operating curve if you have imbalanced data. It's not true. If you distinguish apples and pears, for example, and you have 10% of pears and 90% of apples, you don't really care the type of mistake you do. You kind of, what's important about this receiver operating curve, it does not benefit models which are in favor of one of the classes. So you have to perform equally good for both classes, and then you will get good receiver operating curve. So this one is good, except you care for the minority class much more than you care about the other class. Then the precision recall curve. What happened here? We have the red classifier has a really higher area under curve on this receiver operating curve. You can see it. If you calculate the area, it's a little bit bigger. So we will select the red one. But then we look at the precision recall curve, and we see most of the time the blue classifier provides us really decent, decent recall with higher precision than the red classifier. So we would probably prefer to, if we don't care about this end, it's a bit artificial situation, because at this end the precision drops to 0. But if we care about the recall of 0.6, we prefer the blue classifier over the red classifier. So for severely imbalanced classes, when you care about minority class, use them. This is another example. This is a different prevalence of classes. This is like 50-50. Here, this is 10% of apples, 90% of pears, or vice versa. And this is only 1%. All these rock curves look the same. These are classifiers like different colors, classifiers of different quality. The blue one is the perfect classifier, red one is the random one, and you can see there are something in between. How all these pictures look if you look at the precision and recall. Here they're absolutely equal. Here they look dramatically different. So area under the curve, this receiver operating curve, it can be misleading, but there is no prohibition to use it for imbalanced classes. It's just like what you value more. Yeah. So ROC is not biased like accuracy. Accuracy is like if you predict everything as negative, you can still get good accuracy. In this case, ROC doesn't have this property. It's a good choice, except the case when the minority class is very, very important. Now let's talk a bit about how we evaluate the multi-class classification. It's a bit more, I think, like for me, it looks a bit more heuristic. Here, we have the classes like bird, cat, and dog. And these are results of our predictions. So we had 2 birds, and we predicted one is bird and one is dog. We had 4 cats and predicted all of them correctly, and with dogs and guess you see that we made some mistakes. So we look at the, we can calculate precision. I think now talk about only precision now because it is safe for recall for multiple classes here. So you calculate them separately for each class, this precision here. And then you can calculate several different precisions summarizing this data set, these results of this classifier. Yeah, it's called micro precision. It's you basically take total values from the total values. You don't care about what happened inside the classifier, which classes were predicted fine, which are not. You just take the total numbers. You can call a micro precision. It's just averaging the results between these three classes, and then weighted precision. You weight each class with the weight. Here, when you choose what micro precision. Micro precision, when you look at the total, each like sample, every sample contributes equally. So if you care about this, you choose this. Macro precision is when you want all the classes be equally represented in the final estimation of accuracy. The final estimation of your accuracy I use now not as the statistical metric, but as the colloquial word. Your performance, estimate performance. So micro precision, if you want for the underrepresented classes to be equally presented in your estimation. And weighted is kind of you weight by the weight of the class here. So again, according to your task, everything is changing according to your task. Final thing, I know that you all know what is cross validation. This you said yesterday, what that you all know. But let's briefly discuss. Really, I hope it will be really fast. So the typical approach for machine learning, as you know, is we have data which we train on in the unseen data, and we check performance on the unseen data because we care about the feature prediction. Here, for model selection, it was initially proposed to divide your dataset into 3 parts. One is train, one is validation, one is test. Here, but if you sometimes, it's really often, the datasets are not so huge, and cutting them into these pieces, it may be too expensive for you. So you cut these pieces from your trained dataset. What can help in this case? The cross-validation can help you to find the best model, to estimate the performance of the model, to justify usage of the model that you use there. Yeah, so it belongs to the resampling method. In statistics, there's also bootstrap, and you already discussed the bootstrap yesterday, I think. The types of cross-validations which are mainly used now, like what I've seen, it's leave one out cross-validation, k-fold cross-validation, and repeated k-fold cross-validation. When you really don't have a lot of positive labels, for example, and the just k-fold cross-validation was not enough. You do, for example, 10-fold, and you have only 10 numbers, and they are, for example, really variable there, and you want to be really more accurate in estimation. You can repeat this cross-validation many times and get as many numbers as you want, even though there will be a bit of correlated there. Still, we will do this. In machine learning, like there is no rule. So how you measure the total error? You just average it over the folds. How many folds you get? You average. Which cross-validation you better choose? The one-arm cross-validation, if you use any sophisticated model like deep learning or even the random forest with a lot of predictors, it may take incredibly long. So yeah, in modern machine learning methods, where everything is kind of permuted, there are multiple layers, multiple rounds of updates. One-arm cross-validation can be too expensive, and it's not the only problem here. The other problem is that if we have a large data set and we just throw out only one observation to train, we more or less train on the same data each time. So it's kind of, we see only one model all the time. So it has a really high variance here. So the like statisticians really hate when someone says there is a rule of thumb. They hate rules of thumb. But the rule of thumb here is like do 5-fold or 10-fold cross-validation. It's kind of, I just to show the example. Another thing, you also discussed it yesterday, GLMNet, and this is the integrated part of GLMNet. I really don't know how to use it without cross-validation. It's like now cross-validation becomes part of many methods, so integrative thing already. Yeah, yesterday there was a question, this minimum lambda and the one standard error from it. It's because estimation of the performance is, again, it has confidence intervals here. You see there is confidence, so there is some uncertainty. And to be conservative for future predictions, you may choose this +1 standard error. Here, it's sometimes it's really like in the computational biology I work. The data sets sometimes are not really big because, for example, you study a really rare type of cancer here, and you have small data set and you run GLMnet here, and you see this minimum, but this one standard error goes to 0. So it's here. It basically means that yes, indeed, you have the minimum, but you don't have enough, let's call it significance to say that your model is worth at least something. And this is like the worst situation you can end up. You spend days trying to clean the data set and you end up on this. Indeed, you have minimum. You have, for example, 5 important features and you can report it. But something inside you is like, doesn't agree with this because it's maybe not reproducible. So maybe it's bad science here. But yeah, no one cares. So people take this minimum. But if you see that your 1 + 1 SE is here is around the 0 important variables, 0 important predictors, bad luck. What I recommend in this situation is just like to try to throw away the garbage from the dataset. Predictors which you think don't really matter. Again, in computational oncology, we have hundreds of genes, and going through all of them and looking for literature search, like, can this gene be important for lung cancer, for example? It takes a long time, but there is no other way in this situation. Okay, so let's learn how to do cross-validation. I think everyone knows how to do it, but anyway, let's load the standard data set. It's called Swiss, and the current package, which will give you all the instruments for cross-validation here. 15 minutes left, right? Exactly. So if we did this, should I return? Yeah, just like the data Swiss and library current. Set seed is like its option. It's a good practice. Like always put set seed before you do anything random. If you do it in R&D document, you can put it only on top. There is no need to put it each time when you randomize. Everyone was able to load the current package? Good. How it works? You create object called, I said seed once again. Look how careful I am. Yes. We create an object called train control. Leave one out cross-validation. You basically specify the method, and then you switch in the method. You can call it like random forest or linear model here. So let's. This is data set of fertility of Swiss people in Switzerland, I think. Yes, it's a standard data set. Yeah. So fertility against fertility, I think it's number of children there. Against the dot means all the other predictors together. So leave one out cross-validation uses almost all the sample for training, which in theory should give us best result. Let me know if it works. So let's remember the numbers that we got. R squared is important, even though you know that it's not R squared, it's from random forest. No, it's from linear model, so it's still fine. This one's okay. This root mean squared error, just recorded somewhere that this cross-validation show the performance of your model is something like this. I don't know if exact number, maybe it's different if you use different seed, for example. It worked for everyone, right? Then let's compare it with the tenfold cross-validation. We changed only the object here, only this one. Change it to the method is CV and number, which is false, 10. It's a really powerful method, this train control. It has a lot of methods to train. We just use it for consolidation, but you can use it for many things. There are many features inside. I recommend you in ours, with some if you have free time, you put question and then this train control. It will ask you, do you want default train control or current train control? You select current train control and you read what you can do with this method. It's a really good instrument for evaluation of models. Nothing changes except just the train control. You just replace different, you tell your method to use different cross-validation. So, what's better for you? Which leave one out, which uses the biggest train set, or tenfold cross-validation perform better? To whom tenfold perform better? Smaller RMSE. 1, 2, 3, 4, 5. 6, 7. To whom tenfold perform better than the leave one out? Almost for everyone. Even though the train set was the biggest for the leave one out, you see the tenfold show that it's kind of better. The question is, for example, if you replace method with the RF, with random forest, will it be better? Because random forest technically it shouldn't be so rigid as the linear regression. So it should have kind of, since you have randomization, maybe it will solve the problem. So you need to replace the method. I think method equal LM. You need to put method equal to random forest. There. It's a good time to yeah.
Why do we have different numbers if we have a seed?
Different numbers where?
Like with RMSE and squared for CG.
It's because tenfold cross-validation perform better, the model perform better here. It's smaller, right?
No, I mean, for my part, it's different numbers. It should be the same.
It's different. You may use different architecture. I think it's not architecture independent. I think your generator of pseudo-random numbers, it depends on your processor and your operating system. I think so.
I don't think so.
You don't think so?
You should run set seed always before you run some random things.
Yeah,
like if you run set seed in the very beginning of your script, it will be just.
I think they said just now. You set a random seed before executing this, right?
No, it's the second time.
Only a second. Okay, if you said it before, then it's different. Yeah. I don't know if R is architecture independent. Yeah. In theory, it should take the generator of random numbers from the system. I think that's why people make Docker containers. Yeah. Yes. That's why you make this Bicon, like containers, all this stuff to make it reproducible. Yeah. Okay, so did it work with random forest? Did leave one out cross-validation became now better than the tenfold cross-validation? I don't remember how to you recommend RF or random forest. I think it's random forest. RF, just RF, put RF. And that's why you put this question mark and the train control.
And it's default train.
Yeah. It's default for training, so we must keep that default. So in this, in the random forest, for whom one out consolidation performed better than the tenfold? I think for no one, right? I don't know if you actually did manage to run it. So the whole purpose of this task to show, like at the beginning when I learned this consolidation, I thought that leave one out consolidation is absolutely the best because it trains on the biggest data set. Of course, it should be better in performance, but no, actually no, because the model is kind of it has high variance there. So I hope the idea that you better use like tenfold, fivefold. I hope I was able to show this idea.
What's mean different numbers in random forest result? We have three of numbers.
Three numbers. It's this train control is smarter than we think, and it also makes tuning of hyperparameters inside. So it made already for you tuning hyperparameters there. It tried three different parameters and try. And in 2 days you will have workshop on random forest, and you will finally learn what the try means. But it basically went through different hyperparameters and gave you the best performance with hyperparameter. Not only just consolidation, but also tuning of parameters. Amazing. Use it always.
Random forest is better if you wish to R square, it's higher than LM.
Yes, but random forest with leave one out consolidation and random forest with tenfold consolidation, which is better. Tenfold, still better. Same as for linear model. For linear model, we do the same. You see that here is MRC 7.7, here is 7.5, more or less. And it's not exactly random, you can run it many times, and you get confidence intervals on this, and you will see that it's actually better. So, leave one out consolidation is maybe not optimal choice, even though intuitively it seems the best. The question?
Is it data specific, or in the data set specific, or is the trend data?
I think in general, like if you have really small data set with 20 samples, for example, leave one out makes sense because tenfold. I don't know, like up to you, but I would always try to use tenfold. Maybe in the critically small data sets, you have to use a leave one out. Because otherwise you don't have enough instances to train. So even tenfold sounds kind of reasonable. Yeah. It also may be in the case of not just small sample size, but small number of positive instances. So for example, you have a lot of healthy controls and really small number of diseased people. Then maybe leave one out consolidation can be better because you cannot lose these controls there. They are so valuable for you. Okay, so that's kind of final morale out of the story, the cross-validation, something. The question?
Yeah, how can we assess really like importance of different parameters for us? Like for example, in the dataset speeds, we have fertility, agriculture, elimination, and so on and so on.
This will be covered. It should be covered in variable selection there. So it's kind of a bit out of the scope. That's why I said that we don't do inference now, we do prediction here. We don't care about the features in this framework of like machine learning that we did today. We care only about prediction. And about the interpretability, about which features are important, do a separate workshop. I can also tell, but it will take more time and probably will be slides in this case. So yeah, let's better wait till tomorrow. I think it's tomorrow or the day after tomorrow, something like this. So yeah, this was the idea, and if you have any questions, ask.
Yeah, so the last sentence you said that you don't care about features.
I don't care in interpretability. I don't care about features within this workshop. Otherwise, most of the time in my life, I care only about feature points, not about the prediction. Yeah, it's a philosophical question that we discussed during the panel. And in the clinics, for example, it would be nice to have something that predicts well, even if we don't know what's inside. So I think clinics is already ready to give up the interpretability over the proven performance on independent dataset, as Kasper said. If you use slides for like the CT scans, for example, from the same clinic, it can be a disaster. For the famous FDA approved, I think it was FDA approved, melanoma classifier, as I remember. It was trained on the slides from some clinic, and the most important thing that it was looking for is the the marks that surgeon makes before making the borders of melanoma. They put the marks around this, they take a picture of the melanoma, and then they put it as the learning method. So it was looking at the surgical marks. It was outperforming all the surgeons, because of course it's kind of such a strong feature. And I think if they overlooked this, they were managed to kind of prove it. There was a huge scandal about this. So it's an interesting story. It was published really high there. So, but clinic is already ready to give up into stability. Okay, questions, more questions. Yeah?
What we can do if we have unbalanced classes, how we can perform the consolidations?
When we have what?
Unbalanced classes.
In balanced classes, here indeed it's problematic. First of all, as I said, if you care about the mind-magnetic class, you use other metrics for performance here. And then second, I would say sometimes you cannot solve it sometimes with just with choosing different metric evaluation. You have to choose you have to balance data set internally, for example. It's undersampling, oversampling, so there are techniques which are in addition to choosing the right evaluation metric. You also have to choose the right balance between the classes here. So it's a separate topic. It's a very complicated topic there, and it's topic for the separate workshop, I would say. Yeah, it's one can speak several hours about this thing. Yep.
What do you think about so-called optimally corrected area under curve? Do you know this one?
About what, sorry?
Optimism corrected.
Optimism corrected separating curve, right?
Yeah.
Is it different from this confidence interval approach?
Yeah. So okay, so it's some shade idea, but I see it sometimes in papers. So the idea is to but when you use when you load the model the same data onto strength, it's obviously subjected to
Yes. If you use the same data.
And another example we use to prep for this is to create a model based on subsequent data, so distributed data, and then one use the model of the whole data. And we perform this procedure several times, and then calculate optimism based on, like, I think c-value of model chain of part of data minus c-value of model chain of full data, and based on this you somehow correct for the optimism. I think there's a problem with this, like there's an information leak from the evaluation of full model.
Yes.
The model is published really high, like there's a major communications paper that's used this, and we actually try to write critique of that paper, and the authors are arguing that it makes sense of the data.
So what I would do in this case, like to validate some method, I will take some data set which is huge, which abandoned data, and test this idea using the proper test, separated test. If this optimized correcting area on the curve, is it similar to what you get on the test set in this abandoned data set? And then you can you can simulate data, but in simulated data, of course, it's over it's artificial thing. It's always good to simulate the data, but if you want to criticize some other paper, you need to take real data. I will take some big data set and try the test. If it works, some magical methods from machine learning, they're absolutely shady.
It was actually shown that it's probably.
It has some idea. I understand why they do this, but does it work in this particular context? It should work. Yeah, how accurate it is, that's tough to say. Yeah, so I would just evaluate this separately. I would evaluate it separate data. Yeah, tough to say. Everything which works deserves to live. So if this method works, even the idea is shady, results are correlated with each other, then it can be used. Yeah, it has to be checked if it works in real data. More questions? We can go for lunch, I think. 15 minutes. Yeah. Okay, thanks. Thank you, everyone.